Okay, nobody knows what is Syscall. So basically, if I understand correctly, I'm not operating system developer, but if I understand correctly, it's basically a mechanism that allows a user-land program to jump into kernel to ask kernel to do something, right? Just ask kernel to do something, and then kernel verifies or authorizes a specific operation and does something or just does not something like that, basically. And Linux kernel specifically implements different syscalls, and the one that we're going to take a look at today is called mmap. Yes. And this is a very interesting syscall because it's absolutely unclear what the hell is it supposed to be used for. Well, it says it maps and unmaps files or devices into memory, but if you never did any low-level development, what the hell is that supposed to mean? And on top of that, it takes 6 different arguments, which kind of indicates that this function is extremely overloaded with different meanings. I'm not even sure if I can say like that, but anyway. So yeah, and the problem is this function is extremely versatile. I'm not even sure if I use that word correctly, but I like this word and I'm going to use it in this specific context. I don't speak English anyway. So this function is extremely versatile, and the main problem with learning this function is that you can use it in many seemingly unrelated cases, right? You can use it in many seemingly unrelated cases. Let's take a look at cases which you can use it for. You can use it for allocating memory. You can use it to allocate memory. And you may ask question, why do you need to use mmap to allocate memory if you have malloc? Well, silly you, how do you implement malloc? In fact, malloc is implemented in terms of mmap, which is not 100% true. As far as I know, it's implemented in terms mmap and break, yet another syscall that is outside of the scope of today's video. It changes the size of data segment, whatever that's supposed to mean, effectively increasing the amount of memory the program consumes. So as far as I know, malloc on Linux uses combination of both break and mmap. So yeah, but if you don't have a standard C library, you can, ask Linux kernel just map some pages to me and give them to me without any malloc. And then you can use unmap to unmap them. So what is another thing you can use a map for? You can use it for reading files. Yes. If you worked with standard C library, for you it's completely different activities, allocating memory and reading files. You sort of separate these two activities, but from the Linux kernel perspective, it's pretty much the same thing, because what you're doing, you're mapping a file to a memory, so the content of the file becomes a memory. So there's no much difference between allocating memory, whatever that's supposed to mean, and reading files. You map file into memory, and there you go. So another interesting thing you can use it for is inter-process communication, because mmap has a lot of parameters that let you tweak different properties and permissions of the memory you're mapping, and you can even allocate a chunk of memory that is shared between several processes. So you can use mmap for inter-process communication. You see, we already have 3 different cases that are seemingly unrelated to each other, but they all can be achieved with the same syscall, allocating memory, reading files, inter-process communication. Yeah, this is, nice. Single responsibility principle, go away. Out. Who needs single responsibility principle if you have mmap? Am I right? So, and another 4th case I wanted to mention is it gives you more precise control over permissions. How do you spell it? Precise control over memory, not permissions. I think when we talk about memory permissions, we're talking about protection. protection. Because look, you can specify protection of the memory you're mapping, and it can be read, write, and most importantly, executable. If I understand correctly, if you use malloc, majority of the malloc implementation won't give you executable memory. At least if I had to implement malloc, I would not mark it as executable, because in majority of the cases, if you want to malloc something, you want to just store some data there just to work with the data, and it's going to be a huge security threat if that memory will be executable. So I wouldn't do that, but sometimes this is exactly what you want. Maybe you want to load some instructions and execute them. And we're going to look into that a little bit closer as well today. So this is basically the use cases I know for now. If you know more interesting use cases for mmap, please tell me in the chat or in the comments below if you're watching it on YouTube. Yes, we're going to upload that shite on YouTube. I'm an epic YouTuber. Did you know that? Okay, so and let's take a look at these 4 cases a little bit closer. How about that? For each case, we implement an example program that demonstrates, you know, how it can be used there. Anyway, let's go somewhere. I'm gonna go ahead and create a folder called mmap. And you know what I want to do, chat? I want to use a little bit of magic, of Emacs magic, to turn this into a checkbox list and save it inside of the project folder, todo.org. So we're going to keep track of the implementation of those things. So let's start with allocating memory. Before we go into allocating memory, I need to open a window in the middle of Siberian winter because it's too hot inside. So, very sorry. Oh yeah, nice. Central heating, yes. Literally -22C in Novosibirsk, exactly, because we're programming in C today. You're absolutely correct. So let's create a file called allocating, no, let's actually call it 01 allocating memory, so it looks nice when you actually use ls command. Allocating memory.c. So I'm gonna write a very quick, very simple hello world. Printf hello world. Okay, and we need to create some kind of a building process. Building system. So we're gonna use makefiles for that. Makefile. So I'm gonna call the executable the same as the source code itself, but without the extension. So which compiler should we use today, chat? Should we use GCC or Clang? TCC. I'm not sure. Like TCC, we found a bug in TCC the other day. I'm gonna go with Clang. Okay, maybe GCC. So we're gonna enable all of the warnings, and the output is going to be equal to that, and the input is going to be equal to that. And on top of that, I think it would be very interesting to enable debug information. That's right. So let's give it a try, and let's try to build this shite. It doesn't build because it's not called GDB, it's called GGDB. That's right. So, and let's try to run this program to see if it even prints anything. As you can see down below, it did print a hello world. Absolutely epic, in my opinion. Let's open the mmap man page and see how you can allocate a little bit of memory. I'm gonna go ahead and copy paste this stuff here, and the allocated memory is gonna be put here. Let's take a look at the first argument. The first argument is address. And address, if I'm not mistaken, basically hints the kernel where exactly to map the memory. which is interesting. So malloc doesn't give you that much of a flexibility, right? It doesn't give you that much of a flexibility. It just gives you some memory at a random place. But you can hint the kernel where to place it, and if it's null, the kernel just chooses for you and page align it. So this is exactly what we want, I suppose. We don't really know where exactly we want to put it. So let's just say null. And the next parameter is how much memory do you want? So it depends on what we'll try to do. But as far as I know, 640 kilobytes is enough for everybody. So let's actually allocate this much of the memory. So we specified the place, we don't care about the place, and specified the size. In case of malloc, that will be enough, 100% enough. But for mmap, this is not enough. You also have to specify the protection for the memory. Kibibytes, is it supposed to be called kibibytes? I don't know. I know nothing about computers and memory. I'm really sorry about that. So is 640 kilobytes is supposed to be like this? I don't know. Do I look like a programmer? Anyways, so next one is protection, and protection is just basically a bit mask with that combines 3 protection levels: execution, read, and write. We don't really need execution. We if we want to just work with some data, we can just enable read and write. And the next thing is flags. This one is very interesting. We want to allocate a little bit of memory just for ourselves. We don't want to share it with anybody, and we don't want to back it by any kind of file. And if I remember correctly, for that you have to specify a flag private. So it creates a private copy on write mapping. Updates to the mapping are not visible to other processes. Mapping the same file and are not carried through, blah blah blah. So this is basically what we are expecting. Okay, so this basically indicates that it's not going to be shared by with anybody, but we also have to specify that it's not going to be backed by any file, and for that you're supposed to use map anonymous, if I remember correctly, or just unknown. Yes, map anonymous. The mapping is not backed by any file, blah 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 blah. So yes, so that makes it ignore the fd argument, which is a file descriptor to map the file into memory. So if you say it's anonymous, it's not backed by any file, so it's going to be ignored. But if you don't provide this thing, you'll have to be obligated to provide the file for this thing. And yeah, so we really want to have anonymous here. And the offset is basically offset inside of the file, if I remember correctly. I don't quite remember. It's not that important of a thing. By starting at offset in the file and so on and so forth. So basically it gives you an opportunity to specify offset inside of the file. We don't work with the file. Maybe it's used for something else. You see, it's a very versatile function. But anyway, so this is how easy it is to allocate a little bit of memory using a map. Super easy. Is it not? Love it so much. What do you guys think? So the thing is, how are we gonna test that it works? Well, let's test that it even compiles, because we don't know if it even compiles or not. Maybe I've fucked it up. I'm pretty sure I fucked it up because I didn't even include the correct header. Would you look at that, chat? Will you use free to free it? No. So to free that memory, you're supposed to unmap it. Yes, that's not how it works. Because as already said, malloc uses combination of mmap and break, and I believe because of that, you don't really know at any particular time whether you have to decrease the break or unmap the memory. So this is the information that is only available to the malloc implementation. And yeah, so yeah. Anyways, Does it compile? I don't remember. It does compile, but we don't use a pointer anywhere. So how are we going to test that the memory was actually allocated and we can do something with it? Well, let's just try to do something with memory. One of the examples I can think of is let's just calculate a sequence of Fibonacci numbers inside of the allocating memory and see if we can write to that memory and read from that memory. And Fibonacci sequence is actually perfect because it requires read and write, both of them, from the same memory, because it depends on the previous numbers, so you'll have to read them and write to the next one. So read, write, read, write, read, write, read, write, read, write, read, write. See my point? Okay, so let's allocate n Fibonacci numbers. So how many numbers we want to work with? Let's actually do 10. We're gonna have 10 integers. Let's do the following thing. So allocate enough memory for n integers. And we're gonna instantly cast all of that to a pointer to an integer. So now we have, you know, a memory for 10 integers. I guess after that it makes sense. Yeah. So you have to also keep in mind that a map can fail, right? It can fail. In case of a failure, it will return -1 and will set error no to indicate a specific error. Well, I mean, Syscall doesn't set error no or anything like that. It is done by libc wrapping, right? Calm down, chat. Calm down. Everything's okay. So what I want you to type, in fact, I want you to type assert. Anyway, so let's include assert.h. And what I want to assert is that, well, does it return -1 in case of an error? This is kind of strange. Like, I mean, it returns a pointer. On error, the value map failed, that is -1 casted to a pointer. Or cast. I don't know how to, you know, how to take a past form of cast. Interesting. I thought it's 0. All right. And they even assigned a special, a special macro for this specific value. This is very interesting. So we want to assert that access is not equal to map failed. So we're going to use assert in this particular situation because it's just easier in educational example, but in a real application, you probably don't want to assert something like that. You probably want to actually do an if statement and just print something meaningful to the user. But for our case, we're going to just assert all of these things. Yeah, something like that. Anyways, after that, I want to initialize the Fibonacci numbers. So the 0th Fibonacci number is going to be equal to 0. The first one is going to be equal to 1. So the next one is going to be 1, the next one is going to be 2, the next one is going to be 3, 5, and so on and so forth. Right. What's interesting is that I want to do another assertion here, saying that n should be at least 2 numbers, because you see I'm trying to access first 2 numbers, and I'm making that out of assumption that n is greater or equal to 2. So, and that's why I want to just make sure that everything's okay here. Anyway, after that, let's just calculate the rest of the Fibonacci numbers. How about that? I think it's pretty epic. So 2 less than n. So how do you calculate Fibonacci numbers, chat? Well, ith Fibonacci number equal to the I-1 Fibonacci number plus I-2 Fibonacci number, and there you go. Yep. So after that, after you worked with mmapped memory, right? After you worked with mmap memory, you have to unmap it. What's interesting about unmapping the memory is that you also have to specify the size of the memory you're unmapping. Very interesting, is it not? So, okay, we're gonna do it like that, because it's interesting because malloc and free does not allow you to keep track of the size of the memory. You just can provide the pointer to that memory and the whole memory will be allocated. So apparently the size of the memory is tracked by a malloc implementation, but here you have to do everything yourself, like an adult. All right, so, and I suppose unmap can also return an error. Let's take a look how to handle mmap errors. Mmap. So on success, mmap returns 0. On failure, it returns -1. Okay, so we're gonna assume that error is greater or equal than 0. Something like that. Something like that. Chat. The point of this example is not to demonstrate how to calculate Fibonacci numbers. The point of this example is to work with mapped memory and demonstrate that you can read from that memory and write into that memory. It's not about Fibonacci, Jesus Christ. Anyway, let's try to compile this stuff. Let's try to compile this stuff, chat. Let's try to compile that. Okay, it compiles. It compiles. Write a kernel driver to print Fibonacci numbers. It's a good idea. Maybe we'll try to do something like that. Maybe we even introduce a Syscall to Linux kernel that gives you back and Fibonacci numbers calculated in the kernel space. How about that? That will make this particular example so much easier to implement. Jesus Christ. So it's not really that interesting to run this program because you won't see anything. Well, you may see the exit code though. You may see the exit code, and exit code is successful. It's 0. When it says finish, that means it's 0. You see it's green. So it's not that interesting. So the most interesting stuff can be viewed in the debugger. So chat, let's jump into the debugger. Are you ready? Here we go. Oh, wait, it's not the debugger. I need to go to my folder. Yes. GDB break main. TUI enable run. We are in the debugger, chat. Are you ready for epic hacking? Okay, look. We passed that assert. That means memory was mapped successfully. Let's take a look at the memory. So if we print access, it's just a pointer. Let's actually dereference it and print 10 elements. And you see, all of them are filled with 0. So let's go step. We have to display it as well. I'm sorry, it's not enough. Like I was thinking about displaying. So let's display it. So when you display something, it will be shown on each step. So you see, we initialized first 2 numbers, and here they are in the memory, 0, 1. Let's continue calculating Fibonacci numbers. And as you can see, the memory is filling up with Fibonacci numbers successfully. And that memory is mmapped using mmap Syscall. And the most interesting thing is going to happen right now. We unmapped the memory and instantly GDB is incapable of reading from it. The fact that GDB showed anything confirms that we allocated memory correctly, because otherwise it won't be possible to read from it. Once you unmap it, it's not accessible. You cannot read it. Well, it got a map. Sorry. So, and you can clearly see that in the debugger. It's actually pretty cool. It's actually pretty cool how you can easily see that in debugger. And it was unmapped successfully, and we exited successfully. So yeah, this is how you can use it to allocate memory. Who needs malloc when you have a map? Well, you shouldn't really use a map that often specifically for allocating memory, unless you know what you're doing. Because if you use a map, you're gonna end up with the less portable code. So because your code, this code is probably works only on Linux. But if you use malloc, your code will work on Linux, FreeBSD, any kind of BSD system, Windows, Mac OS, whatever. It will work anywhere where you have a standard compliant C compiler. So yeah, This is probably why you shouldn't use mmap directly, but why should it stop us from learning about this kind of stuff? And furthermore, in BSD system, as far as I know, mmap may act slightly differently. Even if you have a system that has a map, it may be implemented slightly differently and have slightly different behavior. So you shouldn't use it if you want to write portable applications. Just a disclaimer, just a small disclaimer. So keep that in mind, chat. Keep that in mind. So this is how you can use mmap to allocate a bunch of memory. How about that? Epic. Done. Now, let's see how you can read file using a map. So, reading files. Let's implement example that is capable of reading files, chat. Let's implement yet another hello world. Hello world. So I forgot to save to do. So we'll have to add this thing here. You know, it's kind of inconvenient to copy paste this chunk of code every time we add another executable. Maybe we want to turn this stuff into a wildcard. Let me demonstrate you. So what you can do in GNU make, maybe it's not really specific to GNU make, but you can specify some kind of a wildcard, right? Basically like a common rule for a pattern of targets and dependencies. So to refer to a target, you use this combination of characters. To refer to the source, you use this combination of characters. Don't try to find any kind of systems. It's just arbitrary. Don't ask me why it is called like that. Ask make developers. I think they're crazy, but yeah. The only reason I remember these things is because at looks like a target. So it means it's a target, something that we want to achieve. And less looks like you're redirecting in bash into the program. That's why it's a source. So this is the only way I managed to memorize those things. And maybe this is the intended mnemonic, but it's horrible anyway. So it's absolutely horrible. And after that, you can just specify the targets that you want to achieve. This one and this one. All right, and that should be enough. So we won't have to add these kind of targets and rules anymore. The only thing we'll have to do, we'll just have to add executables to the all target, which is phony, I believe. I think you have to mark these kind of targets as phony. Nice. Let's see if it works, chat. I didn't want to do that. Compile, make, and yeah, it compiled it. So if I remove all of the executables now and try to compile it again, it actually compiled both of them. Nice, absolutely beautiful. We might as well go ahead and actually store all of these executables somewhere in exif variable of some sort, and then we can introduce a clean target which removes all of these executables, basically cleans it up. So let's give it a try. If I do make clean, it removes these executables, and if I do make, it rebuilds them again. Beautiful, absolutely beautiful. Love it so much. Anyway, let's try to you know, read from files using mmap. Okay. Mmap. Let's copy paste this stuff again. ptr make install. Should we implement make install? I don't think so. Like, do you really want to install these small educational samples to your system, like system-wide? It doesn't look like a good idea. So what's going to be the address? I guess we don't know. No. And what's going to be the size? And this is where it's going to be very, very interesting. So the size should be equal to the size of the file. So we need to know the size of the file. How can we know the size of the file, chat? Please tell me while I'm closing my window because it's getting very cold. All right. That's right. You use Syscall stat, and this is another Syscall that we'll take a look at today. Stat. It's not that one. My God, this is not what I meant. So apparently there are two stat man pages on my system. So basically what you do, you provide the file path and pointer to the stat structure, and this Syscall fills up that structure with a lot of useful information about that specific file. Let's take a look at the definition of that structure. I think it's defined in man file as well. Here it is. You see? It's a lot of different info about that specific file, but the one we're interested in is called st size, which is total size in bytes. This is exactly what we need. But here's an interesting thing. You have to provide file path, right? You have to provide file path. But on top of that, a map doesn't take a file path. It takes a file descriptor. And to get a file descriptor, you have to use a syscall called open, which opens the file. So you have to use stat to get the size of the file, then you have to open it and put fd there. Well, there is another interesting syscall called fstat, which also takes file descriptor instead of the file path. So what I'm thinking is that I think it would be easier to just open a file with file descriptor and use the same file descriptor to get its size and memory map it. So instead of stat, we're probably going to use fstat because it's just a little bit easier. Yeah, so let's go ahead, chat, and open the file. Let's open the file. So what file are we going to open? Well, I think we can get the file from the command line arguments, right? Let's actually get the file from the command line arguments. So we're going to say that command line arguments have to accept at least two arguments. You know, since we're using assert to check that such things, I'm going to just use assert. So I'm going to assert that RGC is greater or equal to 2. And then I'm going to assign this variable RGV1. So from now on, this is going to be our file path. We're going to put it there. And then we have to provide the flags. What kind of flags we have to provide there? What kind of flags we have? So we usually have flags like O read only, write only, or read write. If I remember correctly, these flags, the modes in which we open the file, should correspond to the memory protection of the mmap. So we're going to, I think we're going to only read the file. I didn't see any point in writing to the file, so we're going to provide read only. Read only. I really like this abbreviation. Read only, wrongly, and read. I don't know. Anyway, so, and then we also want to check for the errors. In case of an error, open returns, I think it returns -1. At least this is what it tells. -1 if an error occurs. Okay, sure. So we're going to assert that error is greater or equal than 0. Maybe it's just, yeah, greater or equal than 0. And it's not error, it's a file descriptor. I really apologize for that. It's supposed to be a file descriptor. So now we finally have a file descriptor, and we can use the fstat syscall to get the size of the file. Let's quickly do that. Let's take this thing and put it right here. So here's the file descriptor. We do have a file descriptor, but we don't have the pointer to the structure. Let's allocate that structure on the stack and provide the pointer to that structure to the syscall. So I suppose in case of an error, it will probably return like a negative number or something. Let's actually double check. Where is the return section? -1 is returned in case of an error. So let's do assert error. And now we have a full description of the file, which we can use to tell mmap to allocate or not allocate or map or something like that. Stat buff st size. I think this is called st size. Okay, so just to get this small number, we had to do 2 additional syscalls. Yeah, because we had to open the file and we had to read the size of it. Yeah, so just to get that small small number. Anyway, let's go back to mmap. Let's go back to mmap. So now we have protection. Since as I already said, I don't plan to write into that file, I think the prot is going to be simply read. We're not going to write anything there. And flags. Okay. In our case, I think it's going to be map private, because I don't tend to share that thing with anybody. But it's not going to be anonymous, because anonymous means that it's not going to be backed by any file. In our case, it backed by the file. Like you see, excuse me, in original implementation, in the memory allocation, we used anonymous because we said that we don't have any file. But here we have file, so only private. FD, we do have FD, and we don't plan to offset inside of the file. There we go, we just read the whole file, and the size of the memory is st size. So now, if what you can do with that memory, you can simply write that memory to standard output or somewhere. For example, we have. Oh yeah, I also forgot to check that ptr is not equal to map failed. It's quite important, quite important. So let's take a look at the syscall read. Syscall read. And we can, yeah, we know the point to the buffer and the size of the buffer. And we can just straight up redirect all of that there. So the file descriptor is going to be std out, if I remember correctly, it's 1. The buffer is pointer and the size is the stat buff st size. And then it returns the amount of bytes. Excuse me. It's right. Oh my god, I confused read and write. Chat, why didn't you tell me that I confuse read and write? My god. So you can read and write. Sure. Luckily, it has pretty much the same signature. Yes, we provide the file descriptor, the buffer, and the size of the buffer is stat buff st size. It's supposed to return, if I remember correctly, it's supposed to return the amount of character written. So we're going to save it and we're going to assert that the amount of written characters is equal to the size of the file. So it's quite important. St size. And after that, I suppose we can unmap the file. We're going to provide the memory and the size of the file. St size. Oh yeah, thank you. It's not FD, it's standard output. My god. I'm a professional software developer. That's right. I'm a professional software developer. Okay. So how do you check for errors in mmap? I don't remember, but I do remember that we had something like that here. Okay, so you simply check that error is greater or equal than 0. So this is how we do that. If I remember correctly, by the way, if I remember correctly, after you mapped the file, you can quite safely close the file descriptor. This is what I remember. So once you mapped it, you can close the file descriptor and forget about it. Write can write less characters than ordered, but it's not an error though. You think so? Maybe. But I think in our case, it doesn't really matter that much. We're not going to work with huge files when that may occur, or maybe that's not the reason why it may occur. Anyway, let's just keep it like that. So let's just keep in mind that this might be wrong. So we're looking at the mmap today, not write. So thank you for saying that. So we acknowledge that this may be wrong, but it outside of the scope of what we're doing. Anyways. So let's see if this stuff even compiles. Let's see. Does it compile? This might be wrong. This is how all professionals that I do with record. Yeah, because it's kind of difficult to make everything 100% correct and sometimes even impossible. Yeah. So we don't have a cert. Yeah, it was not first try. I'm sorry. Open. Oh yeah, and you also have to include all of those include files that are specified in the man pages. Okay, so let's go through the man pages. The first one was open, and this is how many files you have to include for open to work. Maybe not, because it also lists create and open at, maybe, but I'm gonna just include all of them just in case. Because you never know, why not? Let's just include everything. Okay, the next one is gonna be fstat. How much stuff you need to include for stat? Yeah, I guess some of them are already included, specifically types and stats, so the only thing we need to add is unistd. All right, and the next one was mmap. So you also think we have to include stdlib. We're gonna include stdlib, don't worry about it. So let me quickly sort everything, and we might as well also include stdlib. All right, and let's try to build it. So we redefined the error. Well, let's actually just reuse it. Nice. Thank you, compiler. Very cool. Would you look at that, chat? Would you look at that? We just implemented a simple cat using mmap. Let's see if it works. We're gonna try to cat the source code of this application itself. And it successfully did a thing, I suppose. It successfully did a thing. Let's try a very interesting stuff. What if we also mark this thing as prot write? What will happen? What if we will allow to write to that memory? Let's explore a little bit. Let's play with the permission flags and see what kind of results we can achieve. I think it's going to be interesting. All right. It compiles, and let's see what's going to happen. Well, nothing pretty much happened, as you can see. Nothing pretty much happened. But this is because we don't really write into that memory. What if we try to write into that memory? What's going to happen, chat? What do you think? Is there a major difference between what Sonic is trying to create and what cat actually is? Cat works with several files. The origin of the name cat is concatenation. The purpose of a cat is to concatenate files, not to print the file content. It's just sort of a side effect of the primary task is to concatenate files together. Just people usually cat one single file, and it's basically a special case of concatenation of several of them. So this tool does not work with several files. Because what you can do, right, you can cat 0, 1, and this is not what I wanted, excuse me, I wanted only the source code. But on top of that, you can cat also the second file, and it will print it as a single stream of the lines. So we just concatenated them together. Okay, so what we can do with the memory of the file that contains the content of the file? I don't know, let's try to reverse it byte by byte. What do you guys think? Is that a good idea? Is that a good idea to reverse it? Where's your cat sitting? It's somewhere eating somebody. Let's try to reverse it byte by byte. How do you reverse a range of memory, chat? How do you reverse a range of memory? I don't remember. I'm pretty sure we can just start by writing a loop. And I guess it doesn't really make any sense to iterate all of the bytes, right? Because what you usually end up with, right? So you have a bunch of things that you want to reverse, like 0, 1, 2, 3, 4. And what you need to do, you need to swap this element with the last one, then the second element with this one, and leave that element alone. So basically you need to iterate until the half of the array to reverse the array, right? Why reverse versus reading it backwards? We're not reading it, we're writing it. Our goal is to check what's gonna happen when you write there. What are you talking about? Excuse me. Just do chore swap. We'll see. I'm gonna use a regular swap, I think. Okay. So what I'm gonna do, I'm gonna take the size of the file and divide it by 2, I suppose. I guess I don't have to care about the remainder, because if I have any middle element, I basically have to ignore that element, and basically the remainder takes care of itself. So I can just take a half of it of this thing. Floor I. Well, I mean, it's automatically floored. We're doing integer arithmetics. We don't need to floor anything. Floor is needed when you're doing floating point arithmetics, and this is not what we're doing. Anyway, so just integer division is floored by default, by the definition of integer division. Yeah. Anyways, how are we gonna swap all of that? So we're gonna have a temporary element, and we're gonna store ith element to the temporary element. Once we stored ith element, that means we're pretty safe to change that element, and that's the one that we're gonna reassign. So we need to now take an opposite to ith element. So an opposite to ith element is gonna be size of the file minus I minus 1. Can anybody tell me why? Can anybody tell me why? Yeah, it's void star, but this is not the question that I asked. So we're gonna fix that. We're gonna fix a void star really quick. So the point is, we're indexing the elements from the 0, but the amount of elements is actually 5. So if your current element is 0th and you subtract 0 from 5, you end up with 5, which points to the element after the one that you need. And since it points at the element after the one which you need, well, you have to put a -1 there to actually bring it back to 4. So this is basically my logic. It's a pretty naive logic, but it works for me. Okay, so, and after that, you reassign this element to t. So this is a very big expression. Maybe it makes sense to take that expression and just assign it to something like that. Is that a little bit better? Maybe. I don't know. This seems UB-ish. We're safe now. Okay, so we just reversed this thing, and on top of that, we're gonna just print it. Will that modify the file that we provide to this program. Oh yeah, I forgot equals. Thank you so much. And also, again, I have to fix the void situation. So it's going to be character. So let's recompile that. It does not compile because I forgot the semicolon. Okay, so we are modifying the memory mapped file. That's what we're doing. Will that change the file? Will that change the file? Let's find out. Let's find out. So we're going to compile it one more time. And we're going to provide the source code of this thing. We're going to live dangerously. So we don't know if it's going to modify this thing or not. But we are going to modify the source code of this program. And if we screw up, we're probably going to lose the source code of the program. Yeah, there we go. Okay, so it reversed it byte by byte, right? It reversed it byte by byte, but did it change anything? It didn't. It didn't change anything. I just reversed this file. It's the same. And this is because we didn't mark this thing as shared. So we marked it as private, but opposite of private is going to be shared. Let's take a look at the documentation of mmap. So share this mapping. Updates to the mapping are visible to other process mapping the same region, and in case of a file-backed mappings are carried through to the underlying file. To precisely control when updates are carried through the underlying file requires to use msync. We're not going to go into that, but it will work without msync for now. So we have to change private to shared. So you have a private, sort of private copy of the file when you use private, but if you use shared, now you're living dangerously. Now you're living dangerously. Are you guys ready? Are you guys ready to live dangerously? So, is it going to screw up our file now? Mapping failed. Why did it fail? Why did it fail? Why it didn't fail with private, right? It's perfectly fine with private, but it failed with shared. Yes, yes. I've seen you chat screaming that for a couple of minutes already. Yes, I know that. I know that you know. Well, I was just trying to be dramatic. My God, come on. Yes, this is because we didn't open file correctly. And what's funny is that when you have a private mapping, it doesn't really matter because you're not going to modify the file itself anyway. So you just get, a safe copy of the content of the file for your program to work with. But if you share it, well, this is where you're going to have a little bit more careful, have to be a little bit more careful. So let's actually open the file with the correct permissions. I don't remember what kind of permissions we have to put there. Let's find out. So it's have to be read-only, wrongly, and read-write. Okay, so we have to put read-write, if I understand correctly. Okay, so now we can read-write. Let's recompile. It compiled. Will that thing screw up our file now? I'm going to revert to the file in my Emacs. It did. We lost all of our source code. Funny thing, in Emacs I can just undo and save it again, and we're safe again. So yeah. But yeah. So this is how you can read files and even write files. By the way, let me actually update our sheet here. Reading and writing files. Because we just wrote to a file using a mapping. And this is where it gets very interesting. This algorithm knows nothing about file system. Seriously. It only works with a region of memory. But that specific algorithm wrote to a file. So, which means you can use memory map as a perfect abstraction layer. You can implement algorithm that works with the region of the memory, and your algorithm automatically works with files, with some kind of devices, or just memory. So yeah, mmap can be used as an abstraction layer. You can implement generic algorithms, and suddenly that algorithm can work with file, and it knows nothing about the file. Pretty interesting, right? Pretty interesting. Stop miming so very sour. So yeah, abstraction. You everything is memory, maybe even more powerful than everything is a file, because you can memory map file. Okay, so I guess we're done with this kind of thing. So IPC is very interesting. So if I remember correctly, if you create a shared anonymous, so you see so far we created the following combination of flags. Just allocating memory without backing it with a file is private anonymous, right? Private anonymous. Reading from file, just reading from file is just private but not anonymous. Reading writing is shared but not anonymous. What will happen if you do shared anonymous? So it's not backed by file, but it's shared. So this one is backed by file and shared, and that's why we can modify a file. But what if it's not backed by it? Shared memory without any file. So you will create a memory that you can use to communicate between a parent process and child process, which means that you can implement, parallel algorithms and communicate workload between parent and children, like for workers, using that shared memory. So let's give it a try. Let's see how it works. It's going to be interesting. So what we're going to do, I have the following idea. I'm going to create a chunk of memory. Just static memory this time, just static memory. Then I'm going to fork my process, and I'm going to try to modify that memory from the child and see if those changes reflected in the parent. Right, because this is the specific of the Unix systems. You don't have a function create process like in Windows or anything like that. You have a Syscall called fork. And what this thing does, it doesn't even take any arguments. Would you look at that? It doesn't take any arguments. How it's supposed to create a new process with this thing? It clones your current process. So the same code starts to execute in two processes. Yes, and we're going to look into that. It's very interesting. I'm going to show you. And you can also make a fork bomb, of course. No, I'm not going to do a fork bomb, by the way, because this stream is going to be over. So ipc.c. So let's do a hello world. Hello world. Nice. Let's add that thing to the build. IPC, and let's try to build it and see if it's actually built. Okay, looks good to me. So we're gonna define n, the amount of elements for some kind of chunk of memory, right? So the memory is going to be located here in the static memory because it's going to be easier to work with. And let's just go ahead and initialize that memory with something, right? Let's iterate each element and let's assign I+1 to it. So it's going to be initialized with 1, 2, 3, 4, 5 until 10. All right. Okay, and now let's fork the process and try to access that memory from the child. What we're gonna do, to fork a process, you call fork. And fork, according to the documentation, returns you pid_t. So it returns you process ID of the child. But here's the interesting thing. At this point, the execution of the program forks into two processes, but the code remains the same. So basically, it will feel like you started two instances of your program. I'm going to even show you what it's going to feel like. The execution of your program is going to feel like this. I'm not sure if it's a good representation, but I mean, it's pretty much how it's going to feel like. So once execution goes here, you're going to start these two, you're going to have these two things. But in the parent process, fork will return child pid. But in the child, it's going to be equal to 0. Right. So it's going to be the same code, but that specific call when your process forks will return you two different values. And this is the value that you can use to determine whether you are a child or you are a parent. So if you have a 0, that means you're definitely a child and you have to do childish things. I mean, whatever your child process is supposed to do, you got the idea. And if you have a pid, child pid, usually what you do, you just wait for the child to finish or something like that. So let's remove this stuff and do the following thing. We're gonna assign child pid to this. Fork can return -1 on error. Yeah, true, I think. What does it say in the documentation? Let's take a look at them. -1 return on in the parent, no child process. It will return it in the parent. Very interesting. Very interesting. So what we can do here, in fact, we can just assert that child pid is equal to -1. So, yeah. And it's never going to create a child. Yeah, the child is a... Come on. Okay. I mean, I guess I cannot blame you. It's a terminology that was created by the creators of Unix. So they like this kind of terminology. You know, you kill processes, you run demons, you also have zombies. It's a very dark operating system if you think about it. It's a very dark operating system. Anyway, assert.h. Yeah. So, and this is where you're starting to discriminate whether you're a parent or you're a child. So this is the condition that separates children from adults. So if child pid is 0, that means you're a child. Otherwise, you're an adult. I mean parent. So in a parent, I guess you're supposed to wait for the child. You're supposed to wait for the child. How can you wait for a child until it actually finishes? Well, if I remember correctly, there was a syscall something wait. Oh, it wait pid. Would you look at that? We do have it. It wait pid. So it takes the pid that you're supposed to wait for and a bunch of additional options, I suppose. And the cool thing about wait pid is that you can specify -1 for it. And -1 means for any child process, which simplifies the situation a little bit. So you see, -1 waits meaning wait for any child process. Less than -1 means for any child process whose process group ID is equal to the absolute value of PID. Oh, interesting. 0 means wait for any child process whose process group ID is equal to that of the colon. It's all complicated. Let's actually just wait for the child PID because we have a specific PID of the child, so it doesn't really matter, I guess. Yeah, so let's just go ahead and wait for child PID until it finishes up. So the next argument is W status. What is W status? Let's find out. If W status is not null, wait and wait PID stores status information in the int to which it points. So it can be null and will give you more information about what exactly changed. You know, whether it's exited or not, whether it's signal. Yeah, you see, it actually gives you a lot of information about what exactly happened with the process. So you can handle some kind of errors and stuff. Wait PID is an actual function, or did we just make it up? I don't know what you mean by that. Everything is made up. I mean, if it's in a standard library, it's made up by somebody, by the author of the standard. Is that what you mean? I don't understand. Well, I mean, we'll read in the manual page about this function, and if I understand correctly, it's maybe Syscall, but I'm not quite sure. So, well, it looks like, I don't know, it feels like some kind of a Syscall for me, but maybe it is not Syscall. Language in which sorting is programming is made up. Yeah, I agree with it. It's absolutely true, 100%. We made up C. We made it up. Not we, I mean, Kernighan, Ritchie, and Thompson. No, Kernighan didn't do anything, he just wrote a book. Anyway, maybe he did, I don't know. So do we care what exactly happened with the child? I don't think so. So if it died, it died. We don't care. What about the options? What about the options? What are the options? I guess we can just put 0 here. I guess we don't really care about the additional options. So this will allow us to just wait until child is, you know, finished its stuff. Okay. So after that, meanwhile, in the child, we should try to do something, right? Let's try to modify the memory that we sort of share between child and the parent. So we're gonna do our usual algorithm. Let's just reverse it because reversing is super easy to implement. So yeah, it's gonna be n divided by 2 plus I int t x, right? I can actually type it already with the closed eyes, so all right. So in the child, we just reverse the memory, and after that, in the parent, we should try to print the elements to see if they got reversed. So let's iterate the elements. And how are we going to print them? Let's actually print them like so. D and xi. But I want to separate them with a space. So I'm going to do a very interesting trick. I'm going to put a space here, but I'm going to skip one element here and print the first element without the space. Like so. But that requires an interesting assumption that n is at least one element. So we're gonna make that assumption. So yeah, it's quite important to acknowledge that it may break if n is 0, for example. So it's not gonna work perfectly. But at least we don't have any conditions here and it's super fast. Probably. I don't know. So I mean, I cannot use that library there, Alt9, because it's a C++ library and we are programming in C. So yeah, anyway, let's go ahead and see if it's gonna change anything. You know what we can do? What if we print this thing in both child and parent. So we're going to print it in child to confirm that it changed for a child, and we're going to print it in parent to confirm that it maybe also printed in the parent. I don't know. I know nothing about programming. I'm not even a programmer. So I'm going to go ahead and copy paste this thing here to confirm that it was changed. And maybe since we're starting to copy paste this chunk of code, maybe we're going to introduce it as a function called print access. And yeah, just, you know, maybe we're going to do that in multiple places several times just to confirm that everything works correctly. Print access. Print access, and as you can see, yeah, it becomes a little bit more readable. Since we have that in both of the branches, it probably makes sense to put it outside of the branch. So it's basically going to work for both parent and child. You see? Epic, is it not? I think it's pretty epic. But you know what, for better description, we might as well actually add some kind of a prefix saying child, right, and here parent, but that does not contradict to the fact that print access can be put outside of the branches, but for the readability we're not going to do that. And furthermore, to make it a little bit more epic, we might as well put tabs here so it aligns it a little bit more pretty. Okay, so I'm going off tangents, so let's try to compile that and finally see if it does anything. So I forgot to specify the type for this thing, and obviously I also forgot to include a lot of different headers for all of that to work properly. So we'll have to go back to the fork man page and just include these things. Yeah, I'm really glad that man pages actually provide the headers that you have to include for all of that to work. So, all right, the next one, weight pid. Okay, weight pid requires types and weight. Do we already have types? I think we already have types. Yes, we do. So we only have weight. All right. Are you ready, chat? Are you ready? We're gonna start this thing, and you can already kind of see that it didn't work, but you also can see that I forgot a new line. Nice. Let's quickly fix that as well. Forgot the new line. Let's recompile that. I might as well actually run it from Emacs. I think it's going to be a little bit more convenient to run it from Emacs. And here you go. It got reversed for child, but for the parent, it stayed the same. So even though the processes got forked, basically now we have clones of the same processes, they do not share the same memory. They do not. They have their own virtual spaces of memory that don't interfere with each other. And this is where you can use mmap to change that. So here's an interesting thing. So do I already have mmap? So share. So if you provide share but anonymous without backing that with any files, you share this mapping. Updates to this mapping are visible to other process mappings the same region. So what's interesting about that thing is that the addresses, if I remember correctly, kind of stay the same between fork processes, but I might be wrong on that. Please correct me. So the addresses stay the same. But since they are in different virtual spaces, they're sort of isolated between each other. And mmap, if you mapped address in a specific place and marked it as shared, the same address in a different process in a different virtual space is going to be reflected between the processes. Even if you have the same addresses in different processes, they're not going to be pointing at the same memory, as Ayguduk mentioned. They're going to be pointing at different memory because you have virtual addresses that, you know, operating system manages and maps accordingly to isolate processes from each other. But if you map that specific page by with shared flag, the operating system may let you, you know, synchronize those specific regions of memory between the processes so they can share some information. Isn't different page of memory a better term? Probably, I suppose, I guess. Thank you for bringing it up. So, enough theory. Let's go into practice. Let's try to implement that idea. Instead of allocating this thing in static memory, let's just memory map enough memory for this array, and also mark it as shared and as anonymous, and see what's gonna happen. So how are we gonna do that? So I suppose we're gonna basically take this thing here, but it's used by this function. So maybe we're gonna keep it as a global thing. Let's keep it as a global thing. You know, global variables are good, right? Everybody loves global variables. They lead to very maintainable code. Am I right? Anyway, so maybe it would be great to initialize it with 0, but maybe things that are allocated in static memory already initialized with 0. I don't know. I don't program in C. I'm sorry. So what we're gonna do here, we're gonna go to mmap and just bring this thing here. So we're gonna assign that to access. Do we care where exactly we allocate this thing? We really don't. So doesn't matter. The next thing is how much memory? I guess n multiplied by size of integer. Protection. I guess we need read and write, because in this particular situation we read and write, so it's going to be prot read and prot write. Flags, and this is very important thing. Of course, it's going to be shared. We want to share that specific mapping. Do we back it with any file? We don't. Map anonymous. So what's funny is that in majority of the situations, if you use mmap, you only have to remember three flags for mmap. Mmap map shared, map private, and map anonymous. So, and basically it actually answers, so it's sort of like a 2x2 table, right? 2x2 table. Do you want to share this mapping with anybody? Yes, if yes, map shared. If no, map private. So this row answers this question. Very simple one. Do you want to share it with anybody? Yes or no? Yes, shared, no, private. The second question you want to ask, is it backed by a file? If it's not, anonymous. If it is, no anonymous. It's really inconsistent, because in this particular situation you would expect another flag, because in this situation, you see, if you don't want to share it, you have to provide a different flag, but here to indicate that you want a file, you don't have to. So yeah, it's kind of interesting, very interesting design, very interesting design choice. So, and this is probably one of the reasons why this function is kind of, yeah, this is the feelings that I have towards this function. Anyway, so this is shared and anonymous. We don't back it with any file, so 0. We don't offset it because we don't even have any file, but maybe offset is not about files, I don't know. All right, and let's assert that access is not equal to map failed. All right. After that, we do our usual thing. Let's see if it compiles. It's probably not going to compile, by the way. It's probably not going to compile because I forgot to include this particular thing. What's funny is that you need to remember only 3 flags, but mmap has way more flags than that. So it has, my god, shared validate, private, 32 bits, unknown, which is synonym for anonymous and deprecated, so at some point we had unknown, deny write executable, which is ignored, map file compatibility flag ignored. So okay, majority of these flags are sort of compatibility flags and ignored. Maybe majority of them are not even needed, and maybe these 3 that I demonstrated are the main ones that you probably have to use, I guess. Yeah, interesting. We'll see. Okay, I forgot what I was doing. Let's make it one more time. So map failed. Implicit declaration of a map. Oh yeah, I went to the page to actually grab the includes that I wanted to add. Jesus Christ. Okay. Difficult. Yeah, backward compatibility issues. I guess the backward compatibility ruins any API. Yes. So this is sort of like a trade-off that you have to also constantly keep in mind. Do you want to rewrite all of the existing software? If you don't, you ruin your API a little bit. So yeah, it's a constant trade-off. It's a constant trade-off. Unless you rewrite it in Rust, of course. Yes, yes. Okay. It compiles. And let's see if it works. Let's do that in GDB, because in GDB, it's always fun to do things in GDB. Break. Break main, excuse me, break main. To enable. And run. All right. So think was allocated successfully. Let's display it. Let's display access at 10. And here are the elements that we're going to work with. So let's just fill them up. You see, we're filling them up with goodness. Well, just numbers, nothing special. And look at that. We are about to spawn a child process. We spawned the child process and it immediately got reversed because it happened in a separate process. And child process is already long gone because how quickly it's happened. But our parent process is still going, and it's about to wait for child process to change, you know, its state. But child is already gone. Maybe it's zombie right now. It's actually kind of interesting. Is it gone or not? I think it's gone because my htop does not indicate any other additional process. So we have a GDB and O3 IPC. I think it's already long gone. So yeah, anyway. Okay, but we're going to continue. Maybe, yeah, Linux has already cleaned it up, but the fact is our memory already got reversed, and the only way it can get reversed is by child. So yeah, once we forked it, it instantly reversed. And yeah, so here we're gonna wait for PID, and we instantly receive that PID has changed, and we're gonna just print parent. And parent successfully print a reversed one. So you see, we successfully shared memory between parent and child. Isn't it cool? So yeah, basically, if you wanna, you know, implement some kind of like a worker pattern. I'm not really sure if it's a good idea to call it a pattern, but you know, implement a bunch of workers by spawning a bunch of child processes. You can mmap shared anonymous memory and communicate with your children using that memory. For example, if you want to sort the array, you want to implement some kind of like a parallel merge sort. You can split array into chunks, allocate a single process on that chunk, and let those children sort their own chunks, and since that memory is shared, after they're done, that memory, that result of their work is going to be available to you, so you can merge those arrays together, something like that. So basically you can use it for IPC and, you know, inter-process communication and stuff like that. Without p-threads, by the way, without p-threads, you can just use processes. Isn't it cool? I think it's pretty cool. So yeah. All right, I guess we covered the third topic. And let's cover the fourth one. We already covered the fourth one on one of our Twitch streams. But since YouTube people haven't seen it, we're going to do it one more time. As already said, you have a more precise control over memory protection. For example, you can allocate a chunk with executable permissions or executable protection, which allows you to load up some code that will be executed. Let's explore that idea. Let's explore that idea a little bit more. Comparing threads and processes, as far as I know, there is not much difference between processes and threads in Linux. So the only difference, like between them, when you want to create a thread, instead of fork, you use clone. Yes. So clone basically acts like a fork, but it has more arguments to control different settings for the process. For example, you can say that memory between the processes, the whole memory is going to be shared, not only mapped pages, but the whole of them. As far as I can remember, I never really used clone, but if I remember correctly, pthreads uses clone to spawn threads. Yeah, processes has separate memory page. Yes, and that achieved through a more precise settings using clone Syscall. Again, I might be wrong if I remember correctly. What are the trade-offs between using a map between processes and APC using pipes on the std out? It's a good question, and I have no idea, but we can think about it. Because to communicate with a pipe, right? Pipe is basically a file, right? It's a sequence file. So to work with it, you have to use the streaming API, things like read and write, which means they are syscalls, which means that you have to constantly jump between the kernel and userland. And if you have shared memory, you probably don't have to do that. But again, I know nothing about kernel development and stuff like that. I only learned about mmap recently, so I might be saying complete bullshit right now, so don't listen to me. But this is just my logic. So if there are any more professional people out there, please tell me what's the actual difference and trade-offs between these mechanisms. I guess, I don't know. Anyways, good question. It's a good question, I suppose. And I guess from the usability point of view, there is advantage and also disadvantage is that the mmap pages are random access and pipes are linear access. And depends on what you're doing, you might want one way of access over another and vice versa. I guess from that point of view, it makes sense, right? So one is a random access, another one is a linear access. So here's the idea. Let's mmap a bunch of memory that is executable. Let's load up some interesting code into that memory and try to jump into that memory and execute it. That's what we're going to try to do for the fourth example. So, and it's going to be very interesting because we'll have to generate some code. So the question is, how can we generate some code that we can jump to? So yeah, it's going to be interesting. It's going to be interesting, chat. I'm telling you. Okay, it's going to be fourth. I'm going to call it exec. So let's start by writing our usual hello world. stdio printf hello world. By the way, all of that code is going to be available on GitHub after the stream, so yeah, don't worry about it. So if you want to play with this kind of code, everything is going to be available for free. How about that? Do you like free stuff? There you go. You're going to get this code for free. Absolutely useless code though, but anyway. Yeah, exec. Let's try to build it. Okay, seems good. Hello world. All right, so we're gonna try to load to map executable memory, but we need to get the data from somewhere. I suppose we're gonna get the data from the file, which means it makes sense to memory map the file up front. So we're gonna do file memory mapping right now. So I'm gonna go to my example where we read the files. This is actually the binary, not the source code. And just copy paste some code from there. So this is the code that we used, and I think I can safely just copy paste the whole thing. So this entire thing, this is how much code you need to memory map a single file. 16 lines of code. But it's actually way less than you're probably gonna have because we simplified error handling. And if you do care about errors, well, it's gonna be a little bit bigger because you're going to have ifs here and some kind of, you know, stuff, error handling, maybe printing some kind of a useful message and crashing and stuff like that. So we're going to just copy paste this thing here. All right, so, but we're going to slightly change the permissions here. So we don't really care about reading and writing to the file, right? We only care about executing the file. So it's going to be prot exec. So you won't be able to read anything from this file. Do we want to have a shared file? Do we want to modify the file? I didn't think so. So I think I'm going to mark it as private. Do we want to be backed by a file? Yes. So, and because of that, we don't provide anonymous. So the only thing we have to provide here is a map private. All right, good. We're good to go, I think. So in PTR, we have the code. How can we jump into that code? How can we jump there? Well, one way is to probably cast that pointer to a function and actually call that function. So let's give it a try. So we're going to have a pointer, and then pointer to a function, if I remember correctly, looks like this. We're going to cast it to a function that doesn't return anything and doesn't accept anything. Right, so this is basically how it looks like. And then we just call this function. So yeah, as you can see, we're doing some dangerous, horrible, unspeakable stuff. Very dangerous stuff. That's what we're doing. On executable memory, by the way, because we actually explicitly marked it as executable. Very, very dangerous. If some bad code gets into the file, it's gonna get executed. It's gonna get executed from your program. And if your program has some kind of special privileges, well, goodbye. Anyways, let's try to compile this stuff and see if it works or not. Yes, apparently I also forgot to include a bunch of stuff, yes. Assert.h. Oh yeah, let's go ahead to reading file and just copy paste this stuff from there to not waste any time. Okay, everything seems to be compiled. So we need to, I don't want to really run it on random data because it's kind of dangerous. Really don't want to do that. So what I want to do, I want to generate a sequence of x86-64 instructions, put them into the file, and execute them. The question is, why can't I take any executable produced by GCC and use it to execute this program? Why can't I, for example, do this kind of thing and just take, for example, our first example, allocating memory, and do something like that? Why this won't work as I expect? While you're thinking about that, I'm going to go ahead and open a window yet again. Yes, that is right. Because the files produced by GCC are not sequence of instructions. Not only sequence of instructions, they are, if you, for example, do something like file 01 allocated memory, you will learn that they are ELF files. So ELF is a format that serves as a container for CPU instructions. It contains information about how to load the file, how to dynamically link the file, and so on and so forth. It contains a lot of information. And you cannot just take the content of the file and treat it as a sequence of x86-64 instructions, because it's not what these. We can try to extract those instructions from the file by parsing ELF format, but I don't really want to do it right now, and I don't really know how to do it. I mean, it's not that difficult to learn how to do that. I just don't want to do it right now because it's outside of the scope of the video. What I want to do, let's actually generate those instructions directly by writing in assembly. Right. So let's implement a simple hello world in assembly, because this is where assembly is where we can work directly with instructions. Let's quickly do that. Simple hello world. We're going to implement it using elf format as well. And then we're going to strip it down to something that can be compiled as a raw executable that contains only x86-64 instructions. Okay, so first of all, we're going to do a usual elf executable button assembly. Usual elf executable button assembly. So let's do something like, let's call it payload. Yes, that's what it is. When you work with elf executables, you usually have several segments. The two main segments that you usually work with are the text segment and data segment. I'm not really sure if it's specific to elf, but I feel like it is. The last time I looked into elf format, it mentioned different segments, and the names of the segments were, you know, text, data, and so on and so forth. So I assume that when you program an assembly and you specify the segments, they're sort of elf related. Maybe my assumption is wrong. Please tell me if it is. So in the text segment, you usually store the code. The data is usually stored in the data segment, right? Usually when you write an elf executable, you need to have _start symbol, right? And it's going to be the entry point for your program, and you also have to mark it as global symbol. I forgot to mention, the assembly that I'm using here is not really gas or anything like that. It's not a GNU assembly. I'm using an assembly, or NASM. It's my favorite assembly, probably because this is the one that I tried once and it just worked for me, so I have no reason to switch to anything else. So yeah, I think it's nasm.us, this one. Yeah. So this is the one that we're going to use. There's also F assembly, like flat assembly. You can also use GNU assembly. There's a lot of assemblies, but this is the one that I'm going to use. If you use different one, well, leave a comment now and let me know. Let me know. Let's interact with each other. Let's have a conversation. Let's find out which assembler is better. Anyway, so we're going to implement the hello world, and to print the hello world, you have to store the hello world somewhere. Have you heard about Wasm? Yes, I heard about it. I think this is the one that is used by Ben Eater for his X6502 computer. Yes, in his series, I think I saw it. Anyways, we need to allocate some data in the data segment. So we're gonna create a hello label, and we're gonna put some data here. So it's going to be hello world, and we also need to print a new line, but you cannot just easily put \n here because NASM does not support escaping in string literals. So you have to directly put ASCII code of the new line. If I remember correctly, it is just 10, right? If it is not, we'll quickly find out. So yeah, okay, I'm going to keep it as 10. So after that, you have to calculate the size of this memory so you can use it along with write Syscall to print that thing to the standard output. So to do that, we're going to assign a label hello size, and how to calculate it. We're going to use a directive called EQ. I'm not even sure if it's called directive, but what I know for sure is that it produces a compile time value. By using $, we refer to the current address, and we subtract the address of hello from the current address, and that gives us the size of this area of memory. That's right. So, and then we can just use this kind of stuff to, you know, to pass around specifically syscalls. Okay, how to work with syscalls? Well, in assembly, it's super easy. You just call do a syscall instruction. You see, it automatically highlighted it. It's an instruction. But for it to properly work, you have to tell the kernel what kind of syscall you mean. And you usually put the number of the syscall to the rex register. So what I want to do here, I want to put a write syscall, and I need to know its number, but I don't know it. So Google time. And what's funny is that this is an interesting thing. 32 bits and 64 bits syscall have different numbers. 32-bit write has a completely different number than 64-bit write. for some reason, but that's what it is. So what we'll have to do, we'll have to do x86-64 Linux syscalls. This is what we'll have to look for. Okay, Linux syscall table for 86-64. Nice. Thank you, DuckDuckGo. Very cool. Okay, so we're looking for write, and write is 1. Let's actually go ahead and define a couple of macros. So now NASM has a CPP style preprocessor, but instead of hashes, it uses dollars. So we can define something like syswrite, and this is called write. Chat, calm down, everything's okay. Is 1. Yes, it is 1. And it will become a little bit more readable. So you see, and now instead of using like 1, we put a sys right there, and you can clearly see that we're talking about write syscall, and you don't have to look up the numbers. So next, if you take a look at the documentation of write syscall, we have to provide 3 arguments: the file descriptor, the pointer to the buffer, and the amount of characters you want to write. So where do we have to provide those arguments for the syscall? Well, we have to provide them in the registers according to x86-64 Linux call convention. And this is a very interesting thing. Syscalls and regular functions use the same call convention, which makes it super convenient. Anyway, so let's Google it up. I don't remember the call convention of x86-64 Linux, but I mean, DuckDuckGo knows. So let's just DuckDuckGo it. Yeah, Linux x86-64 call convention. I hope it will find it. Isn't write a libc wrapper for the syscall though? Yes, it is a wrapper, because on errors it sets up error no. Error no. It sets up error no. But the syscall itself does not return errors from error no. It returns in the rax, I think. Yeah, I think it returns the result in the rax as a negative number, by the way. What is the calling convention for Unix? What a calling convention? Calling convention. I hope this sys tutorials. Come on. Wikipedia. So where should we go? Wikipedia x86, but I need x86-64. That's the problem, because these conventions are different, and it doesn't even contain Linux, unfortunately. DuckDuckGo doesn't know. Yeah. Okay. Let's maybe Stack Overflow. Maybe they can give us, yeah, syscalls. Oh wait, syscalls may also. I'm an idiot. Chat. This table provided me not only the numbers of the syscalls, but also the conventions that I can use. I'm a professional software developer. Anyways, I hope you will learn from my mistakes, chat. Learn from my mistakes. Okay, so the first one is going to be RDI. This is the one that is going to take the file descriptor. So what is the file descriptor? It has to be standard output. What is the number of the standard output? Let's find out. Well, I know it's 1, if I remember correctly. It's straight up 1. So, yeah. The next one, RSI, is supposed to contain buffer, and this is the buffer. But what's funny is that we're supposed to load an address there, and move does not really suit for loading addresses. What instruction do you use to load an address into a register, specifically RSI? What address do you use, chat? What instruction, I mean? Leah, that's right. But I hope it's gonna work. Yeah, I think it's gonna work like that. Yeah, I think it's just like that. Let's find out. We'll see. We'll see. Next, we have to move the amount of characters. And the amount of characters is what? It's hello size. All right. So we almost successfully implemented the application. The last thing we have to do, we have to call exit syscall. If I remember correctly, for a Linux application, for a proper Linux application, it is not enough to just exit from the function because it has no place to exit to. It has no place to jump to, I think. And it has to call exit so the kernel will kill it. But let's actually find out, what if we don't provide the exit syscall and we just return from start? Just return from start. Let's see what's going to happen. So we need to compile this thing. How do you compile as assembly application with NASM? So, NASM 04 payload ASM. The output, as far as I know, NASM can only generate object file, and then later we'll have to link it using some kind of a linker. And did it just removed my progress, I'm sorry. So it's NASM 04 payload 04 payload ASM, and you also have to specify the format. It has to be ELF64. As I already mentioned, we're starting with ELF application, and then we're going to strip it down to just a row application, a row instruction. Okay, so it successfully translated this thing into object file. So it's a ELF64 bits, least significant. So it's a little endian, relocatable, x86, 64, blah, 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 blah. After that, what you have to do, you have to use LD 04 payload on payload.o. And let's see if it's going to do something. Yes, it actually executed successfully, and now we have 9K executable. So let's actually run it and see what's going to happen. Well, it printed hello world, but at the same time, it segfaulted afterwards. So yeah, it kind of confirms that you have to exit. So if I understand correctly, I might be wrong, but I think the application tries to return back to the caller, but there is no caller. Nobody called this thing. Like the kernel just plays the program and just let it run. So it actually jumped to some kind of wrong address that does not exist. So, and it's segfaulted. So to indicate, for a program to indicate that it finished, it needs to issue exit syscall, so the kernel will unload it and, you know, finalize it properly. So because of that, we'll have to call the exit syscall. Exit syscall is actually quite simple because it takes only one argument. It takes the exit code. Sys exit, and what's going to be the exit call? So I know I can use the same registers here. I know that. So the exit code is going to be 0, and then we just perform the syscall. The question is only, what is sys exit? 60. Okay, so it's 60. 900 bytes to 9 kilobytes. Well, it's going to be even more dramatic than that when we get rid of the ELF format completely. So keep watching. It's actually very interesting. So you won't believe how much just pure sequence of instruction takes. Like it's unbelievable, I'm telling you. All right. You know what? I don't really want to repeat that process over and over again. So let's include the payload compilation into the makefile, but it's going to be a little bit different this time. So it does not really fit into our GCC wildcard, so we're going to have to implement a special process for it. Payload. To compile payload, you need payload object file. Once you have it, what you do, you call linker like that. But to get the object file, you need assembly file, and once you have an assembly file, you compile it like that. elf64, I think it's elf64. Okay, so this is how we do that. Now I'm gonna remove all of this stuff, and I'm gonna try to recompile it one more time. And as you can see, it actually compiled everything correctly. First, it compiled the object file, and then it linked it properly. So now, if I try to run it, it executed successfully without any sig faults, because we exited it. And we also need to add it to clean, but it's kind of interesting because we also need to add object to clean. Well, we can just add this thing to clean, but it's kind of difficult to keep track of. Sure. Clean. So it removed all of the cleans, and then you can build everything, and you can also build everything in parallel. So you see, it basically built everything simultaneously because we have a lot of independent targets. So you see, it's pretty epic, pretty epic. You can use makefile to implement local map reduce. So yeah. Okay, so I showed you that everything works correctly, but this is still an elf executable. This is still an elf executable. So if you take a look at the file, it's an elf executable, but we need to turn it into just a sequence of raw instructions. Well, NASM is capable of generating a sequence of raw instructions. But raw instructions don't really contain any kind of segments, so we'll have to strip off all of this segment stuff because we don't really need it. We're gonna keep everything inside of, like, you know, in the same memory region. So memory region starts here and it ends until here. So basically data is located in the same place as the code. And what you have to do now, you have to compile this thing without specifying the format, because by default NASM will generate a raw binary, which means you don't need to use linker anymore. So you can just directly generate a sequence of instructions from an assembly without any kind of format. It will just give you a sequence of instructions, which is super convenient. So let's find out if it will work or not. It won't work because usually when you need to generate a sequence of instructions, you're probably doing some kind of operating system development, or specifically bootloader development. And usually modern CPU, they usually load up in 16-bit real mode, and then they switch to protected mode and so on and so forth. So usually you need to compile in 16-bit mode. But we're doing x86-64 assembly. So we need to instruct NASM to actually do the same thing, but in 64-bit mode. So for that, if I remember correctly, you use this directive saying that bits 64, and after that it will compile everything correctly. So now we have a file that contains just instructions, and it weighs 51 bytes. So who was talking about 9k bytes of elf executable? So you need 9k bytes to store 51 bytes of instructions. Speaking of overload, by the way. Unbelievable. So, but this thing is, you know, pure instructions. So it just took this stuff and translated it to binary. Strip it. You can. There is nothing to strip. As a matter of fact, everything is already stripped. And if you take a look at in hex editor, you can clearly see hello world is there. It's right up here. Isn't epic? I think it's pretty epic. Okay, and this is suitable to be loaded into executable memory created by mmap and jump to. Are you ready, chat? Are you ready? Let's give it a try. Let's give it a try. Okay. nothing happened. Why nothing happened? Can anybody tell me? Absolutely nothing. So the time has come to troubleshoot the situation. Since we're working with system calls, right? There's a very interesting tool to troubleshoot the program execution. It's called strace. It's called strace. Basically, it takes the program, runs it, and traces every syscall. So we can check if we even call write and exit syscalls, or what kind of syscalls we even call. We can use that to determine exactly where the problem happened. It's super convenient without using any debugger or anything like that. Let's give it a try. It's going to be epic, chat, trust me. So we do strace, remove executable, remove for payload, and here we go. Here's the trace. So here is our mmap. As you can see, we can even look into that. We provided null 51, which is the size of our file, by the way. Our file is 51 bytes, executable, protected, private, and 3. Oh, it's a file descriptor of the file. Then we close the file, and then we called write. And you see, write took 1 as the first argument, which is a standard output, and 13 as the size of the buffer. And as you can see, in our payload, let's take a look at the payload one more time, the amount of characters in the hello world is 12 characters. It's 12 characters plus new line. So that means it actually loaded up payload correctly. But look what happened. What is this address? What is this address? Something is wrong with the address. We load address incorrectly. So you see, we store the code in the same basically memory region as the data. So we need to load it up relatively. And to load a relative address, you have to put this thing here, if I remember correctly. Let's actually check it out. So let's rebuild everything. So we rebuild the payload, and let's try to run this thing yet again. And it printed hello world. Yes. What we just did, we took instructions out of the file, memory mapped it into the memory with protection permission, jumped there and executed the mother flipper. This is the level of protection control memory map gives you. So, yeah. So as far as I know, this is how, for example, just-in-time compilation works. So, you know, interpreters may map protected, map executable memory and just generate x86, 64, or whatever kind of instructions, whatever architecture there is, right in the memory and then jump there and execute it. So this mechanism is quite convenient for just-in-time compilation and stuff. So yeah, this is kind of things you can do there. Can you jump back? Well, if we remove exit, because after exit we cannot jump back, right? Let's remove exit. And let's also go to the example and print something like, we are back. And try it one more time. Hello world, we're back. So we jumped back because we returned. We put return here. So, but it's not going to work with exit syscall, because after exit the kernel will just kill the application. So basically like that. It's very interesting. It's especially interesting in the debugger. Let's actually take a look at how it looks like in the GDB. So I'm going to break main. I'm going to run the application to enable, and let's see how it looks like. So we're okay. Yes, I forgot to provide the file. I'm sorry. Can you do it one more time? Payload. Okay, are we ready? We're ready. Print file path. We got the file path correctly. Let's just load everything up. Let me take a look at the file. I guess I want to cast it to the characters and see what's inside. It doesn't really show me much. I suppose I need to do something like this, maybe. Maybe I don't have to dereference it. Okay, maybe. Ah, it's a binary data. I'm sorry. It's a binary data. But you know, yeah, we'll see. Okay, so we're about to jump into that memory region, but it's kind of impossible to see what's going to happen in the debugger because we don't have a debug information for this thing. So what I'm going to do, I'm going to set disassembly flavor to Intel. First of all, this is a very important step. Otherwise, you're going to have AT&T flavor or assembly, which is disgusting. Okay. Then I'm going to switch the layout to assembly. Now, instead of looking at the C source code, we're looking at assembly that is generated by GCC. And as you can see, we are about to jump to a place that is located in racks. So what is located in racks? Let's take a look at the layout of registers. So in racks, we have this specific address, which looks like a legit address. So are you guys ready to jump there? Are you ready to jump somewhere? I don't know where, but we're going to jump somewhere. Okay, where are we? Move EAX1, move EDI1, LIA, RSI, move EDX, Syscall, doesn't it remind you something? Doesn't it remind you something? Racks are... It's our assembly code. It is our assembly code right here in the memory. We loaded it up, and here GDB actually shows us our code. Well, it's slightly different. It uses different registers, but EAX and racks is pretty much the same stuff. And you can go through it. So EAX is going to be filled with 1 now. You see it's 1 now. Then RDI. We populate everything, and then we call the syscall, jumping into the kernel, and the kernel actually prints hello world for us. Would you look at that? And then we are about to return back into our C code. We're back into our RC code, and if I do a layout SRC, as you can see, we're back at our C code, and we're printing, we're back. So we only printed back, but I guess it got swallowed by GDB or something. So yeah, so it looks especially interesting in the debugger. You can see the loaded payload in the debugger. Well, yeah, so we just looked into different use cases for a map. Let me take a look. Where is the org? Yeah, precise control. We looked at allocating memory, reading, writing files, IPC, more precise control over memory protection, and so on and so forth. I guess it's time to, upload this stuff to GitHub for everybody to play with. What do you guys think? What do you guys think? I think the time has come. So I'm going to remove to do. It's not really needed that much. And we need to git ignore a lot of stuff. And by the way, you don't need this kind of stuff anymore. So we git ignoring these things. Executables, and we git initting everything. Let's commit. So how are we gonna call the repo? I have no idea. Maybe we can just call it mmap or something. Ready, set, go. All right, let's go to GitHub. New mmap. So what is the description? Code examples from the mmap lecture. So I'm gonna call it a lecture, so I feel like a professor explaining to my students complex topics, which is not true, by the way, because it's a very simple topic. Relatively, I suppose. Yeah, what I'm saying is that I like to be delusional. That's what I'm saying. Remote name is gonna be origin. I'm gonna put this thing there. Yes, it's gonna be default thing. Yes, yes. And I'm gonna push it right into the repo. Chat, are you ready? Are you ready? Are you ready? You're ready, chat. You are ready. There we go. Here's your code. So you can play with it. Be careful with reading files. By the way, you know what? I'm gonna actually go ahead to 02 reading files and change shared with map private. So you don't screw up your files just in case. Make 02 reading files save by default. Yeah, there we go. Because it will just straight up screw up your file. Well, I mean, if you call it, you can just call it twice on the same file and it will recover it. But yeah, just in case anyway. So yeah. Okay, that was it, chat. That was it.